Okay, now we want to work out if we have a light bulb putting out a certain amount of power and light, how much will hit something some distance away. Now, people often ask me, how far does light travel? Well, if it's going through something transparent like air or the vacuum of space, light travels as far as it likes. Nothing's going to stop it. However, if you get light spreading out from something like a light bulb, it's spread over a bigger and bigger volume. It's like spreading a small amount of butter over more and more slices of toast. So while the total amount of energy coming out doesn't go down as it goes further and further out, it gets spread over a larger and larger volume. That's why lights need to be near something to light it up. It's not that the light disappears en route, it's just that it gets spread over a larger volume. So we're going to need to define some terms here. The total amount of light power put out, we're going to call the luminosity. I'm using astronomy terminology here. My apologies for this. Light engineers in different fields would use different terminology, but I'm an astronomer, so let's run with that. So luminosity is the total power of the light put out by a source. So for a light bulb, it's about 1 watt. For the sun, it's about 4 by 10 to the 26 watts. So that's the energy put out. And then you want to work out how much energy hits something. We will actually define what we call flux, which is the energy hitting a unit area of the object. So it's the energy hitting a, say, 1 square meter facing directly towards the light source in a unit time. So what we're after is an equation linking luminosity and flux. And that equation is the inverse square law. The basic idea is, if you consider the energy being put out here, and it's going in all directions, it's going to be spread uniformly over a sphere of radius r, where r is the distance of the object from the light source. So, as energy is conserved, the photons are not disappearing, the total amount of energy emitted here must be equal to the flux times the total area of that volume. So the luminosity equals the flux times the total area. Now the surface area of a sphere is 4 pi r squared. That's just saying that all the energy per second emitted from the light bulb must go through a sphere of radius r. The flux is the energy per unit area, so multiply by the area, and that should equal this. And that gives us the inverse square law equation, which is that the flux is equal to the luminosity divided by 4 pi r squared. A very, very, very useful equation for astronomers. Now, why do we call it inverse square? It's because the flux goes as inverse, which means 1 over the distance r squared. So flux is proportional to 1 over distance squared. And there are many such inverse square laws in physics. For example, gravity, the gravitational force, is proportional to 1 over r squared. Electromagnetism, the electric field, is proportional to 1 over r squared. So we'll see inverse square law of fields lots of times in physics. Anyway, in this particular case, let's assume that we've got a 1 watt light bulb and a person 10 meters away. What that's telling us is that the flux of the person is going to be, roughly speaking, 1 watt over 4 pi times 10 squared, which is about 10 to the minus 3 watts per meter squared. So that's how much energy is hitting someone from a light bulb about 10 meters away on the far side of a garden. As it hits someone, some of the light will be absorbed, some will be reflected. Let's for the moment assume that we're reflecting off someone's gleaming white teeth or whites, t-shirt or something, so most is reflected. So if you've got a 1 square meter of shirt, this is the amount of energy that hits it, and most of the energy might also bounce off. If it was a black t-shirt, the energy bouncing off might be much smaller.